Hey friends, welcome back to the channel, and today we're going to go over some tips on how to perform a 3D frame analysis without running into instability errors. We're going to look at global deflection and local deflection, and I'll show you some steps to make sure your 3D model will accurately represent what's going to be built in real life. To start with, I just wanted to remind you to not forget to add the self-weight of the structure. I'm just saying that because some software will not add the self-weight automatically, and it's easy to miss this step. Next, it's important to understand the difference between global deflection or displacement, like Robot calls it, and the member deflection itself. So displacement is the distance from the original position of a point to its final position on the deformed shape, while deflection is the distance from the supports of this beam to a point on the deformed shape. So by looking at the deformed shape of this 3D frame, we can infer that this structure is trying to tip over, and these numbers are the displacement in the X, Y, Z direction. So in other words, they're not only the vertical deflection you would expect from vertical loads. If you want to check the member deflection and assess this number against the code limits like span divided by 250 or 360 or 500 or whatever number you go for, we should check the member deflection, which in this case for bar number 4 is 1 millimeter and not 6 or 5 millimeters. As we mentioned before, the structure is leaning towards the y-axis. So if you have some other structure bracing these columns, you could add a roller support restraining y direction, and that would give you more realistic displacements. So here I applied supports restraining y-axis movement, and that 5 millimeter displacement is gone. On the other hand, if you don't have anything bracing and preventing the frame to tip over, you might need to keep these displacements as small as practicable. Let's make this structure a little bit more interesting. I'm just going to copy some columns and beams up. You can use this intersect tool, which will divide members at the nodes of every intersection. That's a good practice, so you can ensure every node is connected. You can just create a node at every intersection of bars if your software doesn't have the intersect tool. You know that pinned connections are cheaper and easy to fabricate, and it's most likely that you will be using them in the majority of your project. So let's apply pinned release to the end of every beam in the model and run the calculations. We now get several instability errors. This is something you might run into when you first start modeling in 3D in any software. And what we're going to do here is read the errors and try to figure out how to fix them one by one. So the first one, instability in Rx direction in the node 12. What does that mean? If we turn on the local axis, notice that the x-axis is the one along the length of the beam. Rx is then the rotation about x. So what this error is telling me is that the beam is sort of spinning around its own axis. Nodes 1, 4, and 9 are the support nodes. So supports use the global axis. Therefore, it is not Rx anymore, and it's Rz. And it looks like it's happening the same problem, which is the bars are spinning around its own axis. To correct these errors, let's fix Rz in the supports, because we know that in real life our columns won't twist unless you're causing some sort of torsion in the structure. Okay, so where Rz is released, we're just going to fix that and run the calculations. And for the beams, I'll check what robot is releasing for pinned connections. So let's go to geometry, releases. The fixed pinned release has its pinned end with Rx released. Therefore, we're going to untick this box so that twisting doesn't occur. Same applies to the pin fixed release and pin pinned as well. Now note that the calculations will run without any instability errors. Once the 3D model is running smoothly, make sure the bending moment diagrams appear as you expect them to be. For example, a simply supported beam would have no moments at the supports and the peak positive moment in the middle, while for a continuous beam we would expect to have zero moment at the pin connection and negative moment at the side of the cantilever end. Have a look at the deflections as we did in the beginning of the video. Is this displacement looking as you expected? Do you think the structure will deflect this way when under loads? If not, something in the model might be wrong and you need to fix that before going ahead. Check the bar deflections so you can assess the code deflection limits. Looking at bar 11, there is a 2 mm deflection. If the software you're using doesn't show the deflection separate for each axis, a little trick you can use is to apply supports at the ends of the bar, and these will give you the local deflection of that member. So here we get the same 2 mm deflection. And again, we can see that the structure is trying to tip over. However, we may have some sort of bracing in the y direction, and that's why I will restrain this direction so we get displacements that closely match reality. If you think you won't be able to brace this structure, you will have to make sure these displacements are not excessive. Alright fellas, this was not a modeling tutorial, so anything that you learned here you can apply to any software. The principles are the same. If you understand releases, supports, the displacements or deflections, you can do that to any software. The only thing that changes will be the tools or the interface of the software. That's pretty much it, and I hope this video was helpful to you. If you have any questions, just drop a comment below. If you can like the video and share with your friends, and I'll see you next time.